Welcome to the lecture series on object-oriented analysis and design. We have gone through several lectures. We noted only the key words which define what is called an object-oriented paradigm. Terms like reusability, we don't do much of reusability at the level of the programs that are typically developed in our laboratories and academic institutions, but then we should understand that there is something called reusability. We are very clear about those special concepts which make object oriented programming paradigm really distinct from every other methodology, every other paradigm which we have used, namely the polymorphism, inheritance, data encapsulation. In the last set of lectures, recent few lectures, we have looked at multiple varieties of polymorphism, multiple varieties of inheritance, but data encapsulation remains the same. That is the highest goal. We do not really want to do so much of bottom up in a manner where we keep going into the detail like earlier and then completely forget. What we think is we should identify the objects at the earliest, objects to classes, and the progression goes on until we reach the abstraction, which made us very efficient in generalizing the solutions or even in understanding what exactly we want to do. So, what we did is a simple way of first understanding that we need to think differently, that differential thinking or the way to differentiate in terms of thinking stems from what is called classification, from which we learn the idea of class. We should be able to tell that this is apple, this is orange. How they work together, that is something later, but then what we need to understand is keep different things different, keep separation of concerns different. So, by doing this, in the last lecture we have seen, in one of the earlier lectures we have seen that a set of applications like simulation and modeling, user interface design, they have immensely benefited from this approach. It is true that we do not have a complete paradigm that is equally good, equally efficient, equally fascinating for everything that we want to do with computers. However, we know that this particular paradigm, which is the focus of this lecture series, is like this. It is good for this many applications, provided we chose a correct language, we did a good OOAD before that. It is necessary to spend a few minutes to understand that it is the standards that are making us hold for so many years. Years have passed. For 4 decades, nobody thought that object oriented will be such a fantastic idea which will be pulled out of almost pulled out of the the dark spaces, and then suddenly said this is the best idea, sort of a eureka idea kind of a thing. 1950s we had some good papers. 1990 it was more or less becoming a very promising idea 4 decades later. Now again 3 decades later we still bank on this idea, and why are we able to do it? Irrespective of whatever happened in the field of software engineering, we are very clear minded that the usage of standard terms has greatly helped, the usage of standards have greatly helped in giving the longevity. That is essential for us. The more we spend time on these skills which we have already learnt, the easier it will be to make better things happen. So, skilling, reskilling, learning, unlearning, relearning, all these are necessary, but then it is a standardization, a process of standardization that makes us scale faster, that makes us adapt faster, that make us interoperate faster. Otherwise, forever we go back to those terms like requirements, analysis and design, which are so basic to our work, but we do not have a conformance, we do not have a unified view, we keep on having the same old debates, discussions and fights around what do you mean. No, I didn't mean what I said, it's different, what I meant was different. So, standard terms are absolutely essential to progress faster, progress better, more importantly to scale to higher degrees of complexity. 1 lakh lines of code is just the minimum, bare minimum. We are now talking about putting together tens of lakhs of lines of code already developed and then making them into a crore of lines. They are already developed. That is the power which we want object oriented analysis and design to help us out with. There are already pieces of code segments, lakhs of lines, 2 lakhs of lines. The idea of increasing code length and the number of lines is maybe is a bit crude, but then there are so many such pieces which are available. If only you know how to bundle them out together, make a good package or a framework which object oriented is promising, we can build complex software just like that. There are good competitions. For example, for several years in our department, a good friend of mine used to come, Chinjay Bhadauria, he used to come for a Microsoft competition. They had a very nice idea, they simply give pieces of code. He used to come very regularly and discuss also. Pieces of code are given, competitors will simply sit down, wonder which pieces when put together will give a prize winning outcome. It is a good challenge. The same thing that we are talking about, components are all there. The very process is nice. He was operating it on behalf of Microsoft. They have a very good process of identifying those code segments which are quite raw. They are quite raw in that, but then you will have to do some work, do some polish, package them, put together those existing code segments which were available for that particular iteration, for that particular edition of the conference and of the competition, and the teams will simply pick those components that when put together will give them a prize winning idea. It is up to them, they will have to find out. Overnight labs will be open, they can work 48 hours and submit saying that this is what we could do with the available code segments. So, there are so many such competitions, many things are. This is one good sample. Much as you progress, most of you might have already participated. Several professional societies have competitions. Now, at the business level, we want to do that. There are pieces of code, large pieces of code doing some wonderful things. Can we simply put them together and make happen something which is much better, which was not happening? Now, in all these cases, please focus, I am not going to spend much time, but then please do focus on understanding the standardized terms and putting them into use. In teaching, in lecturing, we try to explain, elucidate the concept, but then when you start documenting, it should mean exactly what it is, nothing more, nothing less. So, we give writing a much better focus, a much more concentrated effort and time, because it has to mean exactly the same. So, for the lecturing purpose, yes, this is fine, the flow is fine, we are understanding. We looked at the progress from a puzzle to a problem. Till today, we are not too sure whether we should call what we are doing as problem solving. We are probably helping one another in understanding something called a problem in what we are doing. So, all these questions remain like that. Is it a puzzle that we are solving? Is it a problem that we have defined and hopefully solved? Is it a computer program which is engineered? Engineering is a much later addition. We should now say that puzzle, problem, program. Then we started talking about constraints. Otherwise, we were simply programmers. It takes 10 years to learn programming. Please do read a nice article by Peter Norvig. And it's very good to understand that programming itself is a very involved and an intricate exercise that challenges our minds. People who got into the programming were so enthused and were so challenging, felt so challenged, until we started talking about code generators, automatic code generators, or the beginning was a little earlier when we said that we will only need coding phase. Programming phase is all absorbed very nicely into analysis and design. All that we were trying to talk about programming, most of it is now absorbed into analysis and design. All that we are left with is coding. Then automatic code generators. The charm in a business context to indulge, involve and then keep ourselves enthused in programming is more or less a sort of a bygone era. And then at that time we were talking about engineering, because you can keep on talking constraints, you can keep on talking about test cases, you can keep on doing that program ad infinitum. So we said there must be some constraints outside of the memory and the timing constraints. There must be some other constraints. The business constraints began to loom large, and because of the business constraints we tell that yes, had I been given some more time, I would have definitely come up with a better program, with a better degree of complexity, with a better degree of performance, average case, worst case, best case. We were talking about all that when we were doing programming. Every time you should know what is this algorithm that you have developed, what is the best case space complexity, how much space, how much time, best case, worst case, average case, 3 for time, 3 for space. Then you are doing programming. So gradually what we did was, all this is over in what we called analysis and design of algorithms. We abstracted the idea of programming just a level up and said that analysis and design of algorithms, which hopefully blends with analysis and design phase using some paradigm, and then rest of the story is coding and automatic code generation. Things have evolved. Things have evolved since 68. The way we are doing now is what we are calling as software and software engineering. In fact, software engineering as a term happened first, then we started applying that to the program engineering world, saying that we need to work under constraints, we need to draw a line somewhere. We cannot keep on talking about yes, tomorrow is a better day, tomorrow is a new day, hopefully we'll get more data, more information, hoping that the entire information required will reach is hoping against hope. We just keep it alive, we keep the hope alive. We need to make engineering compromises, we need to make engineering decisions in an area where the analysis and design techniques are not so well groomed, well honed and well cemented like in other engineering disciplines. We are distinctly different. So we started talking about software engineering first, applied the term engineering to program engineering, but still the first term puzzle, the first way in which we started working with the machine computer and gradually moved into what we called problem and problem solving as the central focus. We are probably getting together to define a problem, first completely abstract, take it out of the context, take it out of the domain, take it out of the stakeholder. It does not matter whether it is a developer or whatever it is, we see the problem in its perspective. That is how we began. Then we started moving around. That idea of problem solving has also changed. Program engineering, software engineering. So please do remember that Margaret Hamilton, she was the director of software engineering division of the MIT Instrumentation Laboratory, which developed onboard flight software for NASA's Apollo program. Instrumentation laboratories, or the idea of instrumentation, was absolutely central in all these programs. She is one of the people credited with coining the term software engineering. Her code got humans on the moon and invented software itself. So this is the picture, that is Hamilton. Hamilton in 1969, standing next to the listings of software she had her MIT team produce for the Apollo project. See how many pages, what code has been developed, that much code went into the Apollo mission. So why are we bothered about software engineering? We didn't have the definitions of software engineering. Suddenly on flight or somewhere as it is going, we have a doubt. Somewhere there is a doubt, then we don't know how to browse through all these pages and get it. Well, it had its charm, it had its old world charm, it had that intellectual challenge. Now in November 22nd, 2016, Hamilton received the Presidential Medal of Freedom in the US. These are all nice terms which I have underscored. Barack Obama was the president at that time, and Presidential Medal of Freedom was awarded to Hamilton. So that's the grade of exercise. 1969 she did it for the first time for the Apollo project. 2016 she received this medal. So, what are the terminologies which we are getting focused on? Primarily talk about an approach, talk about a methodology, the highest level. Talk about an approach, methodology, method, procedure, technique. So, this is a kind of an arrangement, an organization. Most of the times we have been with some techniques, those puzzle solving days, some technique is there, some thumb rule is there. He uses some technique and does it, it works, he or she. Technique was dominating our exercises when we were talking about puzzle solving days. Even as a matter of fact, problem solving days, yeah, it works for that fellow, it has done a great job. Will it happen for me also? Well, we will have to find out, we will have to try it out and do it. Then came procedure, all our procedural languages are like that, it is a superset of techniques. Then came method, along with methodology came what we called practices. They are all called best practices these days. Some practices are always useful at a lower level, even though you are addressing the paradigm, the complete paradigm for the small units and for small things, you do not have to bring the entire exercise. Certain practices are legitimately followed, it can be used, and those were becoming best practices. It is more of a management exercise to bring in some practices. And then an approach. An approach describes how language is used and how its constituent parts interconnect. Please remember, in one of the earlier lectures I put one slide comparing 7 languages, object oriented languages. So, that is an approach we have to take. We took an approach which is so language specific. So, if you ask me, everything that I have been talking about is in theory applicable across any object oriented language, but then your syllabus says that C++. So, the approach taken in the courses, most of the time the courses on OAD is C++ based. So, we should not mix up the general concepts with the specific constructs which C++ says, and we should not be locking ourselves to C++. We need to know how to choose a language based on what is it that we are going to engineer as software. That should be the way in which we should take a decision, how language is used and how its constituent parts interconnect, how people acquire their knowledge of the language learning and make statements about the conditions which will promote successful language learning. Language, programming languages do take time to learn, it is not so easy, and for quite some time in good academic institutions the debate was on, should we teach a programming language at all, why should we teach? So, for the sake of familiarity we teach one programming language because they should be more and more focused on the abstraction, not the vehicle chosen that takes them closer to the machine. This is what we claimed will make people become better problem solvers, better engineers. The strength of abstraction is great across all paradigms. Every paradigm needs the abstraction, irrespective of what is the domain that you are addressing. Every paradigm needs abstraction. Object oriented takes you one level above abstraction, call it data encapsulation. Approach sets the general rule of general principle to make learning possible. So, we think that if we learn these, the leftmost column had object oriented concepts. I will show that slide soon after I finish this slide. It typically encompasses both language learning and the language. So, that is what we have understood. Now, what we do is we go back to the working with OO. This is the working step, we have done that exercise. So, they are popular object oriented languages. There is no reason to think that this will be the end or this will be the most consolidated set or a complete set, or just because the corresponding subject teacher liked these languages, he has put no conclusions to be drawn. It is just to give an idea, that is an approach taken saying that most of the syllabi are banking on C++. Why? Because out of this many nice concepts, how many? About 11 concepts which we are talking about, 11 O concepts and 7 languages, C++ is scoring very high on 8. 8 are strong yes on C++. So, we have found an approach. Here we have an approach to making this happen on the machine. It is an approach which we are talking about. So, if that is clear, we will progress further and then move again to the current slide here. So, it typically encompasses both language learning and language. It was not so easy at all. It was not easy to teach computer programming. It is not easy to teach computer language, takes a minimum of a semester, and then we will suddenly realize that that language is out of fashion. We did only Fortran 4 in B, exactly one language. We had some interest and then we learned Pascal. The provisions were made in Usmania. We learned Pascal with laboratory exercises outside of the curriculum and syllabus. These happen. So, the point I want to make is very simple. We need to make it very clear that whatever we do as a choice of a language is better when we have spent adequate time on analysis and design, understanding what we want to do with that analysis and design on the machine. It is at that stage you should get on to an approach. We will take this approach. It supports this, it does this. A methodology, practical explanation of how research is organized, planned. We need to arrive at a methodology of doing this. It cannot happen just like that, cannot be plucked out of nowhere, or it is something which we need to do it in a more concentrated way and a much more better organized manner. Theoretical explanation of underlying assumptions that have gone into designing the research strategy. Methodology is a system of methods used in a particular area of study or activity. So, approach is decided, OAD appears to have done somewhere, now you put a methodology to arrive at methods. The question is, can each one of us do it in our context of work is a big question mark. Until you get a method, you can't think of realization. You can't realize, everything is hazy. A method is theoretically related to an approach organized by the design and practically realized in procedure. The good method recognizes individual differences, provides students learning, facilitates growth and development, achieves the desired results. A procedure is an ordered sequence of techniques which can be described in terms such as first you do this, then you do that, a step by step idea. The procedural way of looking at things. A method at some level is a procedure. Techniques I have spoken, practices I have spoken. Thus, we can conclude that approach is translated into method that contains technique with series of procedures. So, initially we had only 3 ideas. An approach is necessary, a method is necessary, then we go to techniques. Approach is a theory of language. Usually it has to do with the way we express. An approach is holding good as the way we express a phase in software engineering, life cycle phase. How is it expressed? It is an approach. It is a notation, it has a separate team. Ideally, yes, that phase has a completely different notation. A method, an overall plan for the orderly presentation of language material, no part of which contradicts and all of which is based upon the selected approach. The actual implementation in the language classroom or laboratory, I tried to use the terms classroom and student to make it familiar. It works everywhere, classroom or laboratory. We have been talking about trying to have a technique where language teaching happens in the classroom and not necessarily in the laboratory. So, that is one simple example. That is how Anthony's model says. This is what we called lab integrated courses. In theory, there will be a little bit of lecturing, a little bit of an exercise. It is not separate. Practical is not separate, theory is not separate. This is what was a good model, was given by Anthony. Richards and Rodger's model is something which is more closer to us for software engineering. They have first said that method will encompass everything, it touches all, and what they did is an approach, again theory of language, design, objectives, syllabus type, activity types, learner roles, teachers roles, role of materials, procedure, techniques, practices and behaviors, again set into the context of teaching learning. Design will be like this, you have objectives, you can add one more, you can add outcomes, you can have more such things. Procedure, techniques, practices, behavior. So, the idea of object oriented analysis and design can happen in any domain. We can think of it. provided you scope it well. On its own it is not a silver bullet. We do not have silver bullets at all in the field of software engineering. Each time we say that this is a great approach, this is a fantastic method, we keep limiting, saying that at the end of the day we are always looking at best 36% success rate. That is how we have been talking about. So, approach, methodology, method, procedure, technique, this is a set of ideas which we have been toying around. Now, what is the concern here? The concern here is that ideally every one of us who is attempting to make a software engineering exercise happen should start from the scratch. Even though the concepts, principles, the generic ideas are always there, it is how you adapt them makes you succeed or not succeed. You cannot blame anything that is generic. Fantastic ideas are there, life cycle is there, it is known since 85. What is the guarantee that using that life cycle will make your project at hand successful? So, what we keep saying is the same story, saying that you can always pilot a success. It is not possible to replicate it elsewhere until you make it generic and abstract. And when you start making it so generic and abstract and presenting it elsewhere, it is virtually starting over the problem again, except that you have chosen a different language, you have chosen a different lingua franca. So, give me one problem, we will solve it. So, this is what was traditionally called case study based approach for software engineering. It is also necessary, we should understand how from this much of generic ideas of academic caliber will actually make you practical. We talked about books, the principles concept, a book by Pressman which is practitioner's approach, but then what is essential to understand in this entire thing is a case study based software engineering. We know that this problem is solved like this. You can write a very detailed case study. I do remember for some time there were very good schools which were willing to spend time and money on Indian context case studies. It did not really fly. They were willing to give money, and at some point in time a good case study for teaching in software engineering was estimated at somewhere like rupees 2 lakhs, a very old quote, something late 90s, 2 lakhs of rupees for making a fantastic case study. It's quite expensive. That making a case study and teaching based on case study are different ideas, completely different. What we are talking about and what we are taking is a very generic idea which is banking on this. But that is also essential. We should understand what is a case study and how from case study we will abstract. You call it a pilot, you call it a successful story, you call it a case study, whatever you say you call. We can always pilot it based on some techniques, tricks, thumb rules, whatever it is, but then unless you scale it up as a procedure, method, methodology, approach, you do not get that generalization to repeat it elsewhere. More importantly, problems do not appear similarly wherever you go. You will have to understand that there are comparable problems, they are not totally new problems, they are comparable. For that you need abstraction. So, that is the strength of abstraction which we want to build, and if we do it in a manner where, like we talk about typical problems in physics, typical problems in chemistry, that idea of problem is good, we like it as academics. So, we still retain that problem. So, what we need to understand is the fact that it becomes a problem when you are able to spot it across seemingly different contexts, seemingly different domains, but that also means you have come out of the context, you have come out of the domain, you have come out of the stakeholder, but then you should be able to spot it as something similar has happened elsewhere, may not be the exact one. So, you will couch it in different terms, use the approach methodology that fits into the context. So, what we did was at the highest level of abstraction, everywhere you see the same problem, but a few success stories will be there. So many people have tried to adapt, and what we have done is some success stories. We should be careful. Standards, standardized terms in documentation usage is the summary of this lecture. Thank you. We will meet again in